Hello everyone, and today we're going to look at one of our final lessons here on electricity. And for this lesson, one big piece we're going to look at is finding the total resistance of a circuit. So before this, we had an investigation in a lab in which we looked at what are some constants within a series circuit and a parallel circuit. And we found that current is something that is uniform throughout an entire series circuit, and we found that in a parallel circuit, voltage was the thing that was constant throughout the entire circuit. Now, the one thing we haven't mentioned through all those is resistance. Now, resistance isn't going to be constant throughout the circuit because each resistor is going to have a slightly different individual resistance and will have a different impact. But it's really important to be able to find what is that total resistance of that circuit, because that allows us to determine how electricity will flow. Being able to find that current throughout the circuit, it opens up a lot of opportunities for us, and it also allows us to find specific voltages or currents within areas of a circuit. We'll also explore looking at a series parallel circuit, sometimes called a complex circuit, in which it basically is a hybrid of a series and a parallel circuit, and how those now have a mixture of those rules with the constants of current or voltage. And so we want to know, how can we find some of these variables? So the first thing we're going to look at here is finding the total resistance of a series circuit. Now, the series circuits are the simplest to work with, and actually you've already experienced this a little bit when it comes to in that lab. You were able to look at and say, well, we have all the resistors along the exact same path, just like what we have on that image to the right, in which we have all of our resistors along the same path on this circuit. The only direction, or rather the current, has to pass through every single one of these resistors, meaning it's going to be impacted by all of them. You could imagine if we had this circuit and just stretched it out, we'd have the same path like we do here. Okay? Now, because of that, it allows what we do to find that resistance to be a lot easier. We can simply just find the total resistance by adding them all up. We can just take the resistances and add them up. So in this scenario, we had our R1, R2, and R3 at 20 ohms, 30 ohms, and 40 ohms respectively, and that would equal the same as a single resistor at 90 ohms. So basically in that image in the bottom right, if we had that 90 ohm resistor, we could have that one resistor and it would impact that circuit the exact same way as our three individual resistors. Now, parallel is different because there's multiple paths, and because there's multiple paths, it becomes a lot more complicated. So parallel circuits have at least two paths for that current to flow, as we've talked about. We cannot simply add up the resistances like in a series, and that's because there's multiple paths to flow on. And as we explored in that previous lab, when there's a path that has a higher resistance, less current is going to be flowing through it. And that's going to ultimately impact the net resistance of the entire circuit, because not all of the current is going to proportionally go through each spot. All right, so that means we're going to be looking at different ratios in order to determine how that current is flowing. If we have one with a low resistance, more of the current is going to go through there. Not all of it, because, just like a crowded hallway, things like that, there's going to be a point where some of that current is going to go to some of the areas that might be slower to travel through, but are less crowded. It's not the greatest analogy, but just that general visualization. So that really gives us two ways to find the net resistance or total resistance of a parallel circuit. You can see both of those to the right. So the first one is the simplest way, but we can only use it in specific circumstances. So the first way is called product over sum. It's called product over sum because we have multiplication, which can be called finding the product. So if we have that here. And then, of course, sum being that addition. So that's why it's called product over sum. We can only use that, though, if we only have two resistors in that parallel circuit. If we have more than two resistors in that parallel section, then we can't do that. It doesn't work, unfortunately, to treat it in that same way. So this only works for two resistors. Okay? Now, the next way that we can actually do this is the reciprocal formula. And that's what you see on the bottom right. Now this equation looks really complicated, but a lot of it is essentially setting things into ratios and kind of creating a proportion to know how much current is going to go through specific areas. And once we know that, we know how much resistance is going to be into our total. It wouldn't be too different than like in the grade book, you could have a weighted grades. And so like your tests could have a much bigger impact point per point than say a smaller like practice assignment, something where, you know, they can maybe each have 40 points, but one's going to have a bigger weight to each of those points. So each of those points have a bigger impact. Similar type of thing here. Which means when you have 3 or more resistors, we have to use this reciprocal formula. And now you can do more than just the 5 that are there. You could kind of think of this as maybe having like dot, 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 dot. It could go on and on and on to how many resistors you would have in that section. Typically, you're not really going to go past 5. That'd be a lot of resistors in that specific section for the circuits that we're looking at. But you could absolutely apply this to anything greater than 2. You could do this for 2 as well, but the product or sum is going to be a lot quicker for you. So let's look a little bit more specifically into the reciprocal formula. I think this is the one that can be the most confusing at first. I think the product over sum is one that you can generally get. You take your resistances for each and you plug them into their respective spots and then do the calculation. The reciprocal formula, because there's so many parts to it, it can look really confusing. So here's a worked out example for you. So we have the circuit in the upper right hand corner, and what we can see is that we have all of our resistors, and then I drew arrows here down to show where those go in placement of the equation. So effectively what we end up having is once we simplify those fractions into their decimals, so then we are now on to the kind of the third step, if you will, right here. Okay, we now have these decimals, right? Where 1 divided by 5 is 0.2, and you know, so on and so forth, and we have all of these different decimals, add them all up, and then do 1 divided by that. So there's a lot of be careful with the calculations with this one more than anything, because you want to make sure orders of operations are followed. So typically the easiest way is to just convert all of these fractions that we have from up here into decimals, and then sum all those decimals, and then do 1 divided by that sum. And if you do that for this scenario, you'll end up doing 1 divided by 0.369, and you'll end up with 2.7 ohms. That's the net resistance for this entire circuit. Now, one thing you might be noticing with this is, well, hold on, we have a whole bunch of different resistances on there, and our answer is smaller than our smallest one. How can that be? And that's actually something that happens in parallel circuits. They're efficient with current in that way. Because there's so many different paths, if one path becomes overwhelmed, there's just another path for it to take. Because there's multiple ways, it allows for the net resistance to actually be lower than the smallest one. So it actually allows a very efficient circuitry on that front, allowing for that current to flow a lot more freely. And basically, it's like it's avoiding traffic jams. So I know that sounds kind of weird that it can actually be lower, but it absolutely can. So yes, that's absolutely correct. And it just comes down to that overall net efficiency of a parallel circuit. It's one of their properties.